Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. Meinong's paradox, where non-existent objects live. A philosopher named Alexius Meinong proposes a strange theory, a theory about objects that do not exist, and Meinong argues that there are objects that do not exist, but still have properties, can be talked about, can be thought about, and these non-existent objects populate what Meinong calls the realm of being, a broader category than existence, and examples include the Golden Mountain, which does not exist but is golden and is a mountain, and the round square, which does not exist but is round and square, and Sherlock Holmes, who does not exist but is a detective and lives on Baker Street. And Meinong's theory says we can make true statements about these non-existent objects, can say truly that the Golden Mountain is golden, even though no Golden Mountain exists, and this creates paradoxes, creates puzzles about the nature of reference and truth. Because how can statements about nothing be true? How can non-existent objects have properties? How can we refer to what does not exist? And this is Meinong's paradox, the puzzle about non-existent objects, about whether they are real in some sense, whether being is broader than existence, whether there are things that do not exist but still have some kind of reality. And this paradox has generated enormous discussion, has led some philosophers to defend Meinong's theory in modified form and others to reject it entirely, to argue that non-existent objects are impossible, are contradictions, and all objects that can be thought about must exist in some sense. Imagine thinking about Sherlock Holmes, picturing the detective, his deerstalker hat, his pipe, his address at 221B Baker Street, and you're thinking about something. Your thoughts have content, have an object, and that object is Sherlock Holmes. But Sherlock Holmes does not exist, was never a real person, is a fictional character invented by Arthur Conan Doyle. And so, what are you thinking about when you think about Sherlock Holmes? What is the object of your thought? And Meinong says the object is Sherlock Holmes himself, a non-existent object. An object that has properties like being a detective and living on Baker Street but lacks the property of existence. And this seems to make sense of how we can think about fictional characters, how we can make true statements about them, but it creates problems because it seems to commit us to a vast ontology of non-existent objects. All the fictional characters, all the impossible objects like round squares, all the merely possible objects that could exist but do not. And this ontology seems bloated, seems to violate parsimony, seems to multiply entities beyond necessity. The paradox sharpens when we consider impossible objects, objects like the round square, which is both round and square, and these properties are incompatible, cannot both be instantiated by a single object. And yet Meinong's theory seems to allow that the round square is both round and square, has both properties despite their incompatibility, and this violates the law of non-contradiction, seems to allow contradictions to be true. And Russell famously criticized Meinong for this, argued that the round square both exists and does not exist. Exists because it has properties and things with properties must exist to have them, and does not exist because that is part of its characterization. And this contradiction shows that Meinong's theory is incoherent, cannot be accepted, and non-existent objects are impossible, and all talk of them must be reinterpreted as talk of something else, talk of ideas or words or possible worlds, but not talk of actual non-existent objects. Visualize Meinong's ontology as having two realms, the realm of existence containing actual objects, like tables and mountains and people, and the realm of being containing all objects, including non-existent ones like golden mountains and fictional characters, and the realm of being is vastly larger, contains everything we can conceive, all possibilities and impossibilities, and only a tiny subset of being also has existence. And Meinong's theory says that statements can be true of objects in the realm of being whether or not those objects exist, and truth is not restricted to existing objects. And this solves certain puzzles about reference, about how we can refer to what does not exist, but creates the paradox of how non-existent objects can have properties, can be subjects of true predications when there is nothing there to have the properties. One response to Meinong's paradox rejects non-existent objects, adopts Russell's theory of descriptions, which analyzes statements about non-existent objects as existential statements that happen to be false, and the golden mountain is golden becomes. There exists something that is golden and is a mountain, and this statement is false because no such thing exists. And fictional statements are understood as prefixed by an implicit fiction operator. In the Sherlock Holmes stories, it is true that Holmes is a detective, and this preserves the intuition that Holmes is a detective, in some sense, while avoiding commitment to non-existent objects. And this Russellian approach has been standard in analytic philosophy, is the orthodox view, treats apparent reference to non-existent objects as disguised quantification or as occurring within the scope of intentional operators. Another response defends Meinong's theory in modified form, accepts that there are non-existent objects, but restricts what properties they can have, distinguishes between nuclear properties like being golden or being a detective, which non-existent objects can have, and extra-nuclear properties like existing or being thought about, which are different, and impossible objects like round squares have both roundness and squareness as nuclear properties, but do not violate contradiction because they do not exist, do not have instances in reality, and their properties do not need to be jointly instantiable. And this neo-Meinongian approach preserves some of Meinong's insights while avoiding Russell's objection, and various philosophers, including Terence Parsons and Richard Routley, have developed sophisticated neo-Meinongian theories that handle the paradoxes. A third response appeals to possible worlds, argues that fictional and non-existent objects exist in other possible worlds, are possible but not actual, and when we talk about Sherlock Holmes, we are talking about a possible person, someone who exists in other possible worlds, in worlds where Conan Doyle's stories are true, and this preserves the intuition that Holmes is a detective, is a real object in some sense, while avoiding the paradox of non-existent objects, because Holmes is not non-existent but merely non-actual, exists in other worlds. And possible worlds semantics provides a framework for understanding modality and fiction without Meinongian ontology. Meinong's paradox also raises questions about what it means to exist, about whether existence is a property like others or is somehow special, and Kant argued that existence is not a real predicate, not a property that objects have or lack, but is the presupposition of having properties. And this Kantian view seems to refute Meinong, seems to show that non-existent objects cannot have properties because having properties requires existing. But Meinongians respond that this assumes existence is necessary for predication, that only existing things can have properties, and this assumption is precisely what Meinong denies. And the debate continues about whether existence is a property and whether objects must exist to have properties. The golden mountain glitters in imagination, non-existent but golden, and Sherlock Holmes solves cases in fiction, non-existent but a detective, and the round square defies logic, non-existent and impossible, and Meinong's theory says these are real objects in the broad sense of being, and the paradox asks how this can be, how nothing can be something, how non-existence can have properties, and the answers divide philosophers, some accepting Meinong's insights, some rejecting them entirely, and the paradox persists as a challenge to theories of reference and ontology, a puzzle about what we talk about when we talk about what does not exist, and whether such talk requires real objects or can be explained without them, and Meinong's paradox endures as one of the strangest and most controversial problems in metaphysics. A problem about the boundary between being and non-being, about what counts as real, and about whether existence is the only kind of reality or whether non-existent objects have their own shadowy realm of being. Locke's sock paradox. John Locke, the 17th century philosopher, offered a thought experiment about identity and change that has come to be known as Locke's sock paradox, though Locke himself discussed it in the context of broader questions about personal identity and the persistence of objects over time. And the paradox concerns a sock, or in some versions a shoe or a shirt, that is gradually repaired over years until every part of the original has been replaced. And the question arises whether it is still the same sock or whether it has become a different sock. And if it is different, then when did the transformation occur? And this puzzle is closely related to the ship of Theseus, but focuses on everyday objects and the intuitions we have about artifacts, possessions, and the things we use and care about in ordinary life. Imagine a sock that develops a hole, and the hole is darned with new thread, and later another hole appears and is also repaired, and over time the entire sock is patched and repatched, thread by thread, until none of the original material remains. And yet throughout this process the sock has been continuously in use, worn by the same person, stored in the same drawer, and at no point was there a moment when someone discarded one sock and acquired a completely new one. And so there is a strong intuition that it is still the same sock. That identity has been preserved through gradual change. That continuity of use and function matter more than continuity of material. But now consider a variation. Suppose that each time the sock is repaired, the removed material is carefully saved, and eventually someone uses all the original threads to reconstruct a sock, weaving them back together into the original pattern. And now there are two socks, one that has been continuously worn and repaired, containing none of the original material, and one that has been reconstructed from the original material, but which has not been continuously used. And which of these is the original sock? Or are both originals? Or is neither? And different intuitions pull in different directions. Some say the continuously worn sock is the original because it has never ceased to exist, because there is an unbroken chain of identity linking it to the sock that was first worn years ago, while others say the reconstructed sock is the original because it's made of the original material, because material composition is what individuates objects. And still others say that both have some claim to being the original, or that the question has no determinate answer because identity is vague or conventional. Locke used examples like this to explore the conditions of identity over time, arguing that different kinds of things have different criteria for persistence, that a mass of matter is the same mass if it has the same constituent parts, but an artifact like a sock is the same sock if it has the same functional organization, and a living organism is the same organism if it has continuity of life, and a person is the same person if they have continuity of consciousness and memory. And so identity is not a single uniform relation, but varies depending on what kind of thing is in question. The sock paradox raises questions about artifacts and their relationship to their materials, because unlike natural objects, artifacts are defined partly by their functions and purposes. A sock is not just any piece of fabric, but a piece of fabric designed and shaped to be worn on a foot. And so perhaps what makes a sock the same sock over time is not the persistence of the same material, but the persistence of the same functional structure, the same ability to serve the purpose for which it was made. And if this is right, then the continuously repaired sock remains the original, even after all its material has been replaced, while the reconstructed sock, though made of original material, is a replica rather than the original because it lacks the continuity of function and use. But this view faces difficulties too, because it seems to make identity depend on extrinsic factors, on how the sock is used and perceived, rather than on intrinsic properties. And it raises the question of whether an artifact that is stored away unused for years ceases to be the same artifact, or whether a sock that is repaired and then used for a completely different purpose, say as a hand puppet, remains the same sock or becomes something else. The paradox also connects to questions about personal attachment and sentimental value, because people often care about particular objects, not merely because of their function, but because of their history, because of the associations and memories attached to them. And so a sock that has been worn for decades may have sentimental value that a newly reconstructed sock, even if materially identical, would not have. And this suggests that identity, at least in the context of personal possessions, is partly constituted by historical and relational properties, by the role the object has played in someone's life. And this relational view of identity implies that the continuously worn sock is the original because it has the right kind of historical connection to the person who owns it, while the reconstructed sock is a mere duplicate, physically similar, but lacking the history that gives the original its significance. The sock paradox also raises issues about vagueness and borderline cases because, in practice, the transition from original to replica is not sharp. There is no precise moment when the repaired sock stops being the original and becomes something else. And so perhaps the question of whether it is the same sock admits of no determinate answer. In borderline cases, perhaps identity is vague and the law of excluded middle. The principle that for any proposition, either it or its negation is true, fails for identity statements involving gradual change. The paradox has legal and practical implications as well, in contexts where the identity of an object matters for property rights, warranties, insurance claims, or historical authentication. Courts and experts must sometimes decide whether a heavily restored painting or a rebuilt car is the same object as the original or a different object. And these decisions depend on criteria that are often contested, on judgments about how much change an object can undergo while remaining itself. And these judgments reveal that identity is not always a purely factual matter, but involves normative and pragmatic considerations, decisions about what we care about and what purposes our identity judgments are meant to serve. Lockie's sock sits in the drawer, worn and repaired, a humble object that embodies deep philosophical questions, and it reminds us that persistence through time is not as straightforward as common sense suggests, that the boundaries of objects are not fixed by nature, but negotiated through concepts and practices. That identity is a nexus of material, functional, historical, and relational factors, and that the question of whether something is the same thing it was before is often a question without a single correct answer, a question that depends on context, on what aspects of similarity and continuity we privilege, and on whether we are asking about material identity, functional identity, or historical identity. And the sock, like the ship of Theseus, sails on through philosophical discussion, a paradox that will not be mended, a puzzle that remains even after all its threads have been replaced. Morton's fork, when both choices lead to the same doom. A tax collector in 15th century England faces a dilemma when assessing how much wealthy citizens should pay, and the collector observes that some nobles live extravagantly, displaying their wealth openly, and others live frugally, claiming poverty. And Archbishop John Morton, serving as Lord Chancellor under King Henry VII, devises a strategy to extract taxes regardless of which lifestyle the noble chooses, and the strategy is simple and brutal. If a noble lives extravagantly, then clearly they have money and can afford to pay high taxes. And if a noble lives frugally, then clearly they are saving money and must have accumulated wealth and can afford to pay high taxes. And either way, the noble must pay. There is no escape, no strategy that avoids taxation. And this trap, where two apparently opposite choices lead to the same unwanted outcome, became known as Morton's fork, named after the archbishop who wielded it. And the term has entered common usage to describe any situation where someone must choose between two options that both lead to the same undesirable result, where the appearance of choice masks the reality of inevitability. Imagine being a noble in Morton's England, weighing your options, trying to decide whether to live well or live simply, and realizing that either choice leads to heavy taxation, that the tax collector has closed off all escape routes, has constructed a logical trap where your strategy is irrelevant, where you lose regardless of what you choose. And this creates a sense of futility, a recognition that the game is rigged, that the appearance of agency is illusory. And Morton's Fork exemplifies a class of situations where apparent choices are not genuine choices, where different paths converge on the same destination, and the only real choice is whether to accept the inevitable or to refuse to play the game at all. The structure of Morton's Fork appears throughout logic, rhetoric, and strategy. Wherever someone constructs an argument that covers all cases, that shows that regardless of what premises are accepted, a certain conclusion follows, and such arguments can be powerful tools of persuasion, can trap opponents in positions where they cannot escape the conclusion, but they can also be fallacious, can hide implicit assumptions or false dichotomies, can present apparent inevitability that dissolves under scrutiny. And distinguishing genuine Morton's Forks from apparent ones requires careful analysis of whether the two paths really do lead to the same conclusion, or whether there are hidden differences, hidden escape routes. Visualize the fork as a Y-shaped path, two branches diverging, one path representing extravagance and one representing frugality, and both paths lead to the same destination. The tax collector's office and the noble walking either path arrives at the same place. And the fork is not a choice between outcomes, but a choice between routes to a predetermined outcome. And the futility comes from recognizing that movement, that action, that strategy, all are pointless, all lead to the same end, and the only way to avoid the destination is to refuse to walk, to opt out of the entire framework. Morton's Fork differs from a dilemma, where two choices lead to different, undesirable outcomes, and the chooser must select the lesser evil, because in Morton's Fork, the outcomes are the same, are equally bad, and the choice is between different routes to that bad outcome. And this makes Morton's Fork particularly frustrating, particularly demoralizing, because at least in a dilemma there is a meaningful choice, a decision that matters, but in Morton's Fork the choice does not matter. The outcome is fixed, and the appearance of choice is a cruel illusion. The concept has applications in game theory, in situations where a player's strategies are dominated, where regardless of what the player does, the outcome is worse than some alternative the player cannot access, and recognizing Morton's Forks is important for strategic reasoning, for understanding when continued play is pointless, when the game should be abandoned rather than played, because playing only wastes resources without changing the outcome. Morton's Fork also appears in legal and political contexts, where laws or policies are designed to be inescapable, where any action a person takes falls under the law's scope, and this can be legitimate, can reflect comprehensive regulation of a domain, but it can also be oppressive, can create situations where individuals have no legal way to avoid a burden, no option but compliance, and recognizing such structures is important for identifying injustice, for understanding when law has become a trap rather than a framework for freedom. The paradox also has psychological dimensions, because facing Morton's Fork creates learned helplessness, creates the sense that choices do not matter, that outcomes are predetermined regardless of effort or strategy, and this can lead to resignation, to ceasing to resist, to accepting the inevitable, and oppressive systems often work by creating Morton's Forks, by ensuring that resistance and compliance lead to similar outcomes, that fighting and surrendering are equally futile, and breaking out of Morton's Fork requires either finding a hidden third option, a way to refuse the binary choice, or accepting one path and finding meaning in the choosing, even if the outcome is fixed. Some philosophers argue that life itself is Morton's Fork, that all paths lead to death, that whether we live virtuously or wickedly, happily or miserably, we end up in the same place, non-existent, and this can be a source of nihilism, can undermine the sense that choices matter, but it can also be liberating, can free us to choose based on values rather than outcomes. To recognize that if all paths lead to death, then what matters is the path itself, the journey, not the destination, and Morton's Fork becomes an invitation to find meaning in process rather than result. The Archbishop's strategy was effective, was brutal, extracted taxes efficiently, and the nobles paid, unable to escape the logic, unable to find a strategy that avoided the fork. And Morton's Fork entered history, became a term of art, became a warning about inescapable traps, about situations where apparent choice conceals actual constraint, and the fork remains present in contemporary debates about policy, law, and strategy. A reminder that not all choices are meaningful, that sometimes the appearance of freedom masks the reality of compulsion, and that recognizing Morton's Fork is the first step toward escaping it, toward finding the third option, the refusal to engage, the rejection of the binary. And the fork stands, points in two directions, both leading to the same place, and the challenge is to see the fork for what it is, to recognize when choice is illusory, when strategy is futile, and when the only real option is to walk away, to refuse the fork entirely, to create a new path that the fork's designer did not anticipate. And Morton's Fork remains a timeless trap, a logical structure that appears whenever someone seeks to eliminate all escape routes, to ensure that whatever choice is made, the desired outcome follows, and the fork endures as a reminder that the appearance of choice can be deceptive, that freedom requires more than options, requires that options lead to genuinely different outcomes, and that when options converge, when the fork's prongs meet, choice becomes meaningless, and only opting out restores agency. Laplace's demon, the mind that knows everything that will ever happen. A supremely intelligent being, a vast intellect that knows the position and velocity of every particle in the universe at a single instant, stands outside time and space. And this being, this demon, as Pierre-Simon Laplace called it in 1814, possesses the complete laws of physics, the equations that govern how particles interact and move, and with this information, the precise state of every atom and the exact rules of motion. The demon can calculate the future, can determine with perfect accuracy where every particle will be at any future time, can predict every event, every thought, every decision, every outcome, from the fall of a raindrop to the rise of civilizations, from the collision of atoms to the death of stars. And in principle, the demon could also calculate the past, could trace every particle's trajectory backward to determine exactly how the present arose from previous states. And so this demon, given sufficient computational power, could know everything that has happened and everything that will happen. The entire history of the universe, past and future, encoded in a single snapshot of the present. And this is Laplace's demon, a thought experiment about determinism, about whether the universe is a clockwork mechanism, where the future is entirely determined by the past, where free will is an illusion, where everything that will ever happen is already decided, already implicit in the current state of things. Imagine the demon's knowledge as a vast table, infinitely long, listing the position and velocity of every particle, every electron, every quark, every photon, trillions upon trillions upon trillions of entries, and the demon has access to all this information perfectly, knows it exactly, with infinite precision. And the demon also knows Newton's laws, or perhaps Einstein's field equations, or quantum mechanics, knows the rules that govern how these particles influence each other, how forces propagate, how energy transfers, and with this knowledge, the demon can simulate the universe, can run the equations forward in time, calculating step by step how the particles will move, how they will collide and interact, and the simulation produces a prediction, a complete specification of the universe at every future moment. And this prediction, if the laws of physics are deterministic, is not probabilistic but certain. The future is determined, fixed, inevitable, and the demon knows it all. The implications are profound and troubling, because if Laplace's demon is possible, if the universe is deterministic, then free will becomes problematic, becomes perhaps an illusion, because every decision you make, every thought you have, every action you take is the result of particles in your brain following physical laws, and those particles are moving according to rules determined by their initial conditions, and those initial conditions were set by earlier states, going back to the beginning of the universe. And so your choices are not free but predetermined, decided billions of years ago when the universe began, and you are not an agent but an automaton, a complex machine that operates according to fixed rules. And the feeling of making choices, of deliberating and deciding, is a subjective experience produced by computational processes in your brain. But the outcome was never in doubt, was determined from the start. And this conclusion undermines moral responsibility, undermines the concepts of praise and blame, undermines the notion that people could have done otherwise, and it raises the question of what it means to be human if our actions are all predetermined. But Laplace's demon faces several obstacles, several reasons why even in principle it might be impossible. The first obstacle is quantum mechanics, which was unknown in Laplace's time, but is now recognized as fundamental to physics, and quantum mechanics is probabilistic, not deterministic. The Heisenberg uncertainty principle states that we cannot know both the position and velocity of a particle with perfect precision. There is an irreducible indeterminacy, a fundamental limit on what can be known, and when we measure a quantum system, the outcome is random, governed by probabilities but not determined. And so Laplace's demon cannot have the precise initial conditions it needs, cannot know the exact state of the universe, and even if it could, the laws of quantum mechanics only predict probabilities for future events, not certainties, and so the future is genuinely open, not determined, and Laplace's demon is impossible. The second obstacle is chaos sensitivity to initial conditions, where tiny unmeasurable differences in starting states lead to vastly different outcomes over time. Weather systems, planetary orbits, fluid flows, all exhibit chaotic behavior, where prediction becomes impossible beyond a certain time horizon, because errors in measurement, no matter how small, grow exponentially and eventually dominate. And even if quantum mechanics were not an issue, even in a classical deterministic universe, practical prediction would be impossible for chaotic systems, and the demon would need infinite precision, infinitely accurate knowledge of initial conditions, and any finite approximation, no matter how good, would fail after sufficient time. And so the demon's predictions would be useless for complex systems on long time scales. The third obstacle is computational. Even if the demon had perfect information and deterministic laws, simulating the universe requires computing power, requires processing the interactions of every particle, and the universe contains roughly 10 to the 80 particles, and computing their evolution requires resources. And some physicists have argued that simulating the universe would require a computer as large as the universe itself, and such a computer could not run faster than the universe it simulates, could not predict the future faster than the future unfolds. And so the demon could not tell you tomorrow's events before tomorrow arrives, and the demon becomes useless as a predictor, reduced to a mere recorder that reconstructs what has already happened, rather than foretelling what will happen. Visualize the universe as a vast machine, gears turning, particles moving, and Laplace's demon standing outside, watching the machine, knowing the position of every gear, the velocity of every component, and calculating how the machine will continue to turn. But the demon is blocked by quantum uncertainty, cannot measure the gears precisely enough, is blocked by chaos, cannot maintain accuracy over time, is blocked by computational limits, cannot perform the calculation fast enough, and so the demon, mighty as it seems, is impossible. The universe resists total prediction, resists complete knowledge, not because of practical limitations, but because of fundamental features of physical law and determinism, even if it were true, does not grant us the power to predict. And the demon remains a thought experiment, a symbol of a kind of knowledge that cannot exist, a vision of omniscience that is ruled out by the nature of reality itself. Laplace's demon also raises philosophical questions about explanation and understanding, because even if we cannot predict the future, even if determinism fails or the demon is impossible, we still seek to explain why things happen, to trace causes and effects, to understand the mechanisms that generate events. And this explanatory project does not require Laplacian determinism, does not require perfect prediction, but only patterns, regularities, laws that hold approximately, and science proceeds without the demon, without omniscience, by finding partial explanations, probabilistic models, statistical regularities, and these are sufficient for understanding, for technology, for navigating the world. And the demon's impossibility does not doom science but liberates it, frees it from the burden of total prediction, allows it to focus on what can be known rather than lamenting what cannot. The demon sits in conceptual space, all-knowing and impotent, knowing everything but unable to act, unable to exist, blocked by uncertainty, by chaos, by computation, and Laplace's vision of a deterministic clockwork universe fades, replaced by a more subtle picture, a universe governed by laws but not wholly determined, open to chance, to randomness, to emergence, where the future is not written in the present but unfolds through processes that are partly lawful and partly random, and free will, though not proven, is at least not obviously refuted, and moral responsibility, though challenged, survives because even if determinism were true, even if all actions are caused by prior states, we still distinguish between actions that flow from deliberation and those that do not, between agents who respond to reasons and those who do not, and these distinctions matter, ground our practices of praise and blame, and Laplace's demon, impossible and paradoxical, remains a touchstone in debates about determinism, free will, and the limits of knowledge, a thought experiment that has shaped centuries of discussion and continues to challenge our understanding of what it means to predict, to know, and to be free. Grandi's series, when adding numbers, forever gives multiple answers. A simple mathematical series begins with 1 minus 1 plus 1 minus 1 plus 1 minus 1, continuing forever without end, alternating between adding 1 and subtracting 1. And the question emerges, what does this infinite sum equal? What value does it approach as more and more terms are added? And the paradox is that different methods of calculation give different answers, each seemingly valid, each following mathematical rules, yet reaching contradictory conclusions. And this is Grandi's series, named after the Italian mathematician Guido Grandi, who studied it in the early 18th century. And the paradox reveals fundamental questions about what it means to sum an infinite sequence, about whether all infinite series have definite values, and about the limits of algebraic manipulation when dealing with infinity. Consider the series visually. Imagine a number line where you start at 0, then move 1 unit to the right to reach 1, then move 1 unit to the left back to 0, then 1 unit right to 1 again, then 1 unit left to 0, and this pattern continues forever, oscillating between 0 and 1, never settling down, never approaching a limit in the traditional sense. And so, from this perspective, the series does not converge, does not have a sum. The partial sums bounce between 0 and 1 eternally and never stabilize. But now consider a different approach. Group the terms in pairs, taking 1 minus 1 as the first pair, which equals 0, then 1 minus 1 as the second pair, also 0, and so on. And the series becomes 0 plus 0 plus 0, continuing forever. And the sum of infinitely many zeros is 0. And so by this grouping method, the series equals 0. And this seems like a valid manipulation. Grouping terms is a standard algebraic operation, and yet it produces a definite answer where the oscillating view produced no answer. Now consider another grouping. Start by leaving the first one alone, then group all subsequent pairs, so the series becomes 1 plus the quantity negative 1 plus 1, then the quantity negative 1 plus 1, and so on. And each grouped pair equals 0. So the series becomes 1 plus 0 plus 0 plus 0, continuing forever. And this equals 1. And so by this different grouping, the series equals 1 instead of 0. And both groupings seem legitimate. Both use standard algebraic rules, yet they produce different answers, 0 and 1. And this is the heart of Grandi's paradox, that the series is sensitive to how it is manipulated, that rearranging or regrouping terms changes the result. And this suggests that the series does not have a well-defined sum in the ordinary sense. Mathematicians have developed sophisticated tools to handle divergent series, like Grandi's, and one approach is Cesaro summation, which assigns values to series by averaging the partial sums. And for Grandi's series, the partial sums are 1, 0, 1, 0, 1, 0, continuing to alternate, and the average of the first n partial sums approaches 1/2 as n grows large, because roughly half the partial sums are 1 and half are 0. And so by Cesaro summation, Grandi's series equals 1/2, and this method produces yet another answer, neither 0 nor 1, but the midpoint between them. And this answer has a certain aesthetic appeal. It represents the average behaviour of the series, the value around which it oscillates, and it can be justified by analogy to functions. If you consider the geometric series 1 minus x plus x squared minus x cubed and so on, which converges to 1 over 1 plus x for absolute value of x less than 1, and you plug in x equals 1, you get 1 over 2. And so in some extended sense, Grandi's series can be said to equal 1/2. The paradox reveals that divergent series do not have sums in the way convergent series do, that assigning values to them requires making choices about what summation method to use, and different methods give different results. And there is no single correct answer, but rather a family of possible values, depending on the context and the techniques employed. And this multiplicity is not a flaw in mathematics, but a feature, a recognition that infinite sums are more subtle than finite sums, that operations that work for finite cases can break down or become ambiguous when extended to infinity. Grandi's series appears in physics and engineering, in Fourier analysis, where oscillating sums arise naturally, in quantum field theory, where divergent series are regularized using techniques similar to Cesaro summation, and in signal processing, where alternating patterns must be analyzed. And in these applications, the choice of summation method is guided by physical considerations, by what gives useful predictions, by what aligns. With experimental results, and the paradox becomes less troubling, less a contradiction, and more a reminder that mathematical tools must be adapted to fit the problem, that formal manipulation must be tempered with judgment about what makes sense in context. The series also appears in philosophical discussions about infinity, about whether infinite processes can be completed, about whether the phrase, sum of infinitely many terms, has a determinate meaning or depends on conventions and choices. And Grandi's series suggests the latter, that infinity introduces ambiguities that finite mathematics avoids, that extending concepts from finite to infinite is not automatic but requires care, requires new definitions, requires acceptance, that some questions have multiple answers or no answer at all depending on how they are framed. Imagine watching someone walk back and forth on a path, taking one step forward, then one step back, then one step forward, then one step back, forever without stopping, and you're asked where they end up, and the answer is that they do not end up anywhere. They continue oscillating. But if you ask where they are on average, you might say they're halfway between the two endpoints. And if you ask where they are after an even number of steps, you say at the start, and after an odd number, you say one step forward, and none of these answers is wrong. Each captures a different aspect of the situation, and Grandi's series is similar. Different questions about the series have different answers, and the paradox arises from expecting a single answer when the situation is inherently ambiguous, when the infinite oscillation resists reduction to a single number. The series continues, 1 minus 1 plus 1 minus 1, terms alternating forever, and the sum is 0 or 1 or 1/2 depending on how you calculate it, depending on what method you use, depending on what question you're really asking. And the paradox endures, a simple series that exposes deep issues about infinity, about summation, about the limits of algebraic manipulation, and about the need for careful definitions when dealing with infinite processes. And Grandi's series remains a teaching tool, a cautionary tale, a reminder that infinity is subtle, that divergent series require special handling, and that mathematics is not just calculation, but interpretation, not just following rules, but understanding when rules apply and when they break down. And the series oscillates, forever unresolved, forever producing different answers, and the paradox persists, elegant and instructive, a monument to the strangeness of infinity and the care required when extending finite concepts to the infinite realm. Maxwell's demon, the tiny creature that could break the universe. Imagine a box divided into two halves by a partition. The partition has a small door, operated by a tiny intelligent being, a demon as physicist James Clerk Maxwell called it in 1867. And the box contains gas molecules bouncing around randomly, some moving fast and some moving slow. Hot molecules and cold molecules mix together, and the demon, perched at the door, watches the molecules approach and makes decisions. When a fast-moving hot molecule approaches from the left, the demon opens the door and lets it pass to the right. And when a slow-moving cold molecule approaches from the right, the demon opens the door and lets it pass to the left. And when molecules moving in the wrong directions approach, the demon keeps the door closed. And over time, this sorting process concentrates hot molecules on the right side and cold molecules on the left side, creating a temperature difference without any energy input, just the demon's intelligence and careful timing. And once a temperature difference exists, it could be used to run a heat engine, to extract work, to power machines. And this seems to create energy from nothing, seems to violate the second law of thermodynamics, which states that entropy always increases, that heat flows from hot to cold, and never the reverse without work being done. And so, Maxwell's demon presents a paradox, a thought experiment, where intelligence appears to defeat fundamental physical law, where information and cleverness seem to allow perpetual motion. And this puzzle troubled physicists for over a century, until the resolution emerged from understanding the relationship between information and thermodynamics. Visualize the demon at work, watching molecules approach, each molecule carrying kinetic energy, moving at some velocity determined by temperature. And the demon perceives each molecule, measures its speed, decides whether to open or close the door, and executes the decision perfectly. And after many such operations, the gas on the right is hotter than the gas on the left. Entropy has decreased in the gas. Order has emerged from disorder, and this seems impossible because the second law of thermodynamics is supposed to be universal, supposed to apply to all closed systems, and the box with the demon should be a closed system. No energy enters or leaves, and yet entropy decreases, and if entropy can decrease, then the second law is violated, and if the second law can be violated, then all of thermodynamics collapses. Heat engines could run at impossible efficiencies, refrigerators could cool without power input, the universe's arrow of time could reverse, and physics as we know it breaks down. The resolution emerged gradually through the work of several physicists, including Leo Szilard, Leon Brillouin, and Charles Bennett, and the key insight is that the demon must gather information about the molecules, must measure their velocities, must store this information in memory, and these operations have thermodynamic costs. The demon's brain or computer or measuring device must interact with the molecules to measure them, and this interaction dissipates energy, and more importantly, the demon's memory fills up with information about past measurements, and eventually the memory must be erased to make room for new measurements. And Rolf Landauer proved in 1961 that erasing information has a fundamental minimum thermodynamic cost. Erasing one bit of information requires dissipating at least a certain amount of heat proportional to temperature. And this heat generation increases the entropy of the environment. And when the entropy increase from information erasure is included in the accounting, the total entropy of the system plus demon never decreases. The second law is preserved. The demon cannot create a perpetual motion machine because the cost of gathering and erasing information exactly compensates for the entropy decrease in the gas. Imagine the demon's memory as a tape with bits that record whether each molecule was fast or slow, and as the demon sorts molecules, the tape fills up. 0 for slow molecule, 1 for fast molecule, and the tape grows longer and longer, and eventually the demon runs out of memory space and must erase the tape to continue operating. And the erasure process, Landauer showed, must dump heat into the environment, must increase entropy elsewhere, and the entropy increase from erasure is at least as large as the entropy decrease from sorting, and so the net change in entropy is 0 or positive, never negative. And the second law holds: the demon cannot beat thermodynamics. Intelligence and information do not provide a loophole. They are themselves subject to thermodynamic constraints, and information is physical, has energy costs, has entropy, and cannot be manipulated freely without thermodynamic consequences. The paradox and its resolution have profound implications for computer science, for the theory of computation, for the relationship between information and physics. Because Landauer's principle establishes that computation has fundamental physical limits, that there is a minimum energy cost for irreversible operations like erasing bits, and this cost sets a lower bound on the energy consumption of any computer. And it explains why computers generate heat, why data centers require enormous cooling systems, why information processing is not free, and it unifies information theory and thermodynamics, showing that bits and entropy are connected, that forgetting information has thermodynamic consequences, that memory erasure increases disorder in the universe. Maxwell's demon also appears in discussions of the arrow of time, the question of why time flows forward, why we remember the past but not the future, why causes precede effects. And the second law of thermodynamics provides an answer: entropy increases, and this increase defines a direction for time. And if Maxwell's demon could violate the second law, then the arrow of time could reverse, the past and future could become symmetric, and the resolution of the demon paradox reinforces the second law, confirms that entropy really does always increase when all systems, including observers and their memories, are accounted for. And this grounds the arrow of time in fundamental physics, connects our subjective experience of time's flow to objective thermodynamic processes. The demon has also inspired practical research into nanoscale systems and molecular machines, because modern technology approaches the scale where Maxwell's demon scenarios become relevant, where individual molecules can be manipulated, where quantum effects and thermal fluctuations dominate, and researchers have built experimental realizations of Maxwell's demon using feedback control, using sensors and actuators to sort particles or extract work from thermal fluctuations. And these experiments confirm Landauer's principle, confirm that information processing has thermodynamic costs, and they explore the limits of miniaturization, the minimum size and energy consumption of computers, and the ultimate efficiency of engines and refrigerators. The tiny demon sits at the door, watching molecules, sorting them, concentrating energy, and for a moment it seems to defeat the second law, seems to create order from chaos. But the illusion fades when the full system is considered, when the demon's memory and the information it gathers are included, when the cost of erasure is accounted for, and the second law stands, unbroken, universal, and the demon, far from being a threat to thermodynamics, becomes a tool for understanding it. A thought experiment that revealed deep connections between information and entropy, between computation and physics, between what we know and what we can do, and Maxwell's demon endures, not as a paradox, but as a solved problem with profound implications, a puzzle that took over a century to fully resolve, and a reminder that even the most abstract thought experiments can illuminate fundamental truths about the physical world, about the nature of information, about the limits of what is possible, and about the deep unity between different branches of physics, between thermodynamics and information theory, between entropy and knowledge. And the demon remains, a fixture in physics pedagogy, a symbol of the power of thought experiments, and a monument to the principle that information is physical, that knowledge has costs, and that nothing, not even intelligence, escapes the iron laws of thermodynamics. Nagel's bat problem: why you can never know what it's like to be anything else. A philosopher contemplates a bat hanging upside down in a cave, navigating through echolocation, emitting high-frequency sounds and listening to the echoes, building a sonic map of the world. And the philosopher asks what it is like to be a bat. What is the subjective character of bat experience? What does echolocation feel like from the inside? And philosopher Thomas Nagel argues that no amount of objective information about bat neuroscience, about bat behavior, about the physics of sonar, can tell us what bat experience is like, because subjective experience has an essential first-person character, a what-it-is likeness that cannot be captured from the third-person objective perspective of science, and the gap between objective description and subjective experience is unbridgeable. And this means that consciousness, at least in its subjective aspect, resists scientific explanation, resists reduction to physical terms. And this is Nagel's bat problem, presented in his famous 1974 paper, What Is It Like to Be a Bat? And the problem illustrates the explanatory gap between physical facts and phenomenal facts, shows that subjective experience involves something that objective science cannot capture, and challenges physicalist theories of mind to explain how subjective character could be accommodated within a purely physical framework. Imagine trying to know what echolocation is like, trying to understand bat experience from the inside, and you learn all the objective facts. Learn about the bat's auditory system, about how it processes echoes, about which brain regions are involved. And this knowledge is real, is valuable, tells you how echolocation works, but it does not tell you what it feels like, does not give you access to the bat's subjective experience, to the phenomenology of navigating by sound. And Nagel's point is that this gap is not due to practical limitations, not due to insufficient technology or incomplete knowledge, but is a fundamental gap between objective and subjective perspectives, between what can be known from outside and what can only be known from inside. And no amount of objective knowledge can bridge this gap, can provide access to subjective experience. The bat problem generalizes beyond bats to any creature with a different sensory modality, a different nervous system, a different form of consciousness. And Nagel uses bats because they are mammals, are relatively similar to humans, yet have a sensory mode, echolocation, that humans lack. And this combination makes the example vivid, makes the gap between human and bat experience clear. And if we cannot know what it is like to be a bat, then we certainly cannot know what it is like to be a fish, an insect, an octopus, creatures whose nervous systems and sensory worlds are even more alien. And this suggests that consciousness, in its subjective aspect, is fundamentally private, is accessible only to the being who has it, and different kinds of consciousness are mutually inaccessible, cannot be fully understood from outside. Visualize the subjective character of experience as the view from inside, the first-person perspective, the what it is likeness. And this perspective is essential to consciousness, is what makes consciousness consciousness rather than merely information processing. And Nagel argues that physicalism, the view that everything is physical, must either deny that subjective character exists, which seems false because we all know from our own case that consciousness has a subjective character, or must explain how subjective character could be physical, how objective physical facts could constitute subjective, first-person experiences. And this explanation is what physicalism has not provided, what the bat problem challenges physicalism to provide. One response to the bat problem accepts the explanatory gap, but denies that it shows anything metaphysical, argues that the gap is merely epistemological, is about the limits of what we can know, rather than about the nature of reality, and consciousness might be physical, even though we cannot fully understand it from the objective third-person perspective. And just as we cannot know what it is like to be a bat, we also cannot know what it is like to be another human, cannot fully access their subjective experiences, and yet we do not conclude that human consciousness is non-physical. And so the bat problem shows limits of knowledge, but not limits of physicalism, shows that subjective experience has aspects that resist objective description, but not that these aspects are non-physical. Another response argues that future science might bridge the gap, might develop ways of understanding subjective character objectively, might create theories that capture phenomenology in physical terms, and our current inability to imagine how this could be done does not prove that it cannot be done. And Nagel's argument trades on current ignorance, assumes that the gap is permanent when it might be merely temporary, and this response is optimistic about the prospects for physicalist explanations of consciousness, believes that the hard problem and the bat problem will eventually be solved by scientific progress. A third response from Nagel's position argues that the bat problem reveals something deep about the structure of reality, that consciousness has an irreducibly subjective aspect, an aspect that cannot be captured by objective physical description. And this does not mean consciousness is non-physical in the sense of being immaterial or supernatural, but it means that physicalism, as traditionally conceived, is incomplete, misses something essential about consciousness, and a complete theory of reality must include both objective physical facts and subjective phenomenal facts. And these two kinds of facts cannot be reduced to each other. And this position is sometimes called naturalistic dualism, accepts that consciousness is natural, is part of the natural world, but denies that it is reducible to physics. The bat problem also has implications for artificial intelligence, for whether machines could be conscious, because if we cannot know what it is like to be a bat, then we also cannot know what it is like to be a computer, cannot know whether AI systems have subjective experiences, and the bat problem suggests that behavioral evidence is insufficient, that even if a machine passes every behavioral test, exhibits intelligence, responds appropriately to stimuli, we still cannot know whether there is something it is like to be that machine, whether there is subjective experience behind the behavior, and this creates a permanent epistemic barrier, a limit on what we can know about machine consciousness. The bat hangs in the cave, emitting sounds, perceiving the world through echoes, and its experience is alien, is inaccessible to human understanding. And Nagel's question remains, what is it like? And the answer is we do not know, cannot know, because knowing requires access to the subjective perspective, requires being the bat or having the bat's sensory and cognitive capacities, and neither is possible. And so bat consciousness remains a mystery, remains forever beyond human comprehension. And this mystery is not unique to bats but applies to all consciousness, to the fundamental subjectivity of experience, to the what it is likeness that defines phenomenal consciousness, and Nagel's bat problem endures as one of the most influential thought experiments in philosophy of mind, a vivid illustration of the explanatory gap, a challenge to physicalist theories, and a reminder that consciousness, in its subjective aspect, resists objective description, resists scientific reduction, and remains one of the deepest puzzles about the nature of mind and reality. And the bat flies through the cave, navigating by sound, living its bat life, having its bat experiences, and what those experiences are like remains unknown, remains unknowable. And the problem persists, the gap between objective knowledge and subjective experience, the difference between knowing about consciousness and knowing consciousness from the inside. And Nagel's question echoes, what is it like to be a bat? And no answer comes, no answer can come, and the problem stands as a permanent marker of the limits of objective understanding, the irreducible subjectivity of experience and the mystery at the heart of consciousness. Richard's paradox. In 1905, the French mathematician Jules Richard discovered a paradox that strikes at the heart of how language and mathematics interact, revealing that certain kinds of definitions can generate contradictions no matter how carefully they're constructed. Consider the set of all real numbers that can be defined in a finite number of words using the English language. And this set seems reasonable at first because most numbers we ever think about can be described in some way. Pi is the ratio of a circle's circumference to its diameter. The square root of 2 is the length of the diagonal of a unit square, and so on. Since there are only finitely many words in the English language and only finitely many ways to arrange them into sentences of any given length, there can only be countably many such descriptions, which means there are only countably many real numbers that can be defined in this way. Yet the real numbers are uncountable, as Georg Cantor proved, which means there must exist real numbers that cannot be defined in any finite number of English words, numbers that are forever beyond the reach of language, numbers that exist but cannot be named or described or pointed to in any way. Now comes the paradox. Consider the real number defined as follows. Let it be the first real number in the set of all real numbers that cannot be defined in a finite number of English words, arranged in some standard ordering, such as numerical order. This definition appears to successfully define a specific real number, and the definition itself uses only a finite number of English words, which means the number it defines belongs to the set of numbers that can be defined in a finite number of words, but the definition explicitly states that the number belongs to the set of numbers that cannot be defined in a finite number of words, and so the contradiction emerges, sharp and unavoidable. If the number can be defined, then it does not belong to the set of undefinable numbers, but the definition picks it out precisely as a member of that set. And if it cannot be defined, then the definition fails to refer to anything at all, and yet the definition seems perfectly coherent, grammatically correct, and mathematically precise. Richard's paradox exposes a fundamental problem with the concept of definability, the idea that we can cleanly separate describable objects from indescribable ones, because the act of describing the indescribable creates a loop that collapses into contradiction. Some logicians argue that the phrase cannot be defined in a finite number of words is itself vague or improperly formalized, that it mixes informal natural language with formal mathematical concepts in a way that generates confusion, and that a more rigorous treatment would prevent the paradox from arising. Others suggest that the paradox reveals a hierarchy in language, that definitions must be made within specific formal systems, and that talking about all possible definitions requires stepping outside the system into a meta-language, and that mixing these levels is where the contradiction appears. Alfred Tarski developed this idea into a full theory of truth and definability, showing that no language can fully express its own semantic concepts without risking paradox. that truth and definability must always be relativized to a particular formal system, and that higher-order languages are needed to talk about lower-order ones. Richard's paradox also influenced the development of computability theory, because the question of whether a number can be defined in a finite number of words is closely related to whether it can be computed by a finite algorithm, and paradoxes like Richard's helped clarify the distinction between computable and non-computable reals. The paradox remains a haunting reminder that language, even mathematical language, has limits, that not everything that exists can be captured in words, and that the boundary between the describable and the indescribable is not as stable as it first appears. Russell's paradox. In the year 1901, a young mathematician named Bertrand Russell discovered a contradiction so profound that it shattered the foundations of mathematics and forced an entire generation of logicians to rebuild their discipline from the ground up. And this contradiction became known as Russell's paradox, a simple question about sets that revealed a fatal flaw in the way mathematicians understood collections and categories. A set is merely a collection of objects, and sets can contain anything: numbers, colours, ideas, even other sets. And at first this seems harmless enough. A set of all chairs, a set of all prime numbers, a set of all books ever written. Some sets contain themselves as members and some do not. And this too seems straightforward. A catalogue of all catalogues would include itself because it is also a catalogue, while a list of all fruit does not include itself because a list is not a fruit. Russell posed a deceptively innocent question. Consider the set of all sets that do not contain themselves. Does this set contain itself? And the mind stumbles immediately into contradiction. If the set contains itself, then by definition it should not contain itself, because the rule states it only includes sets that do not contain themselves. But if it does not contain itself, then it must include itself, because it fits the criteria perfectly. And so the paradox loops without end, a perfect logical knot that cannot be untied. This was not merely a clever riddle or a philosophical curiosity, it was a disaster for mathematics, because at the time, mathematicians believed they could organize all of mathematical knowledge using set theory, a system proposed by Georg Cantor that treated sets as the fundamental building blocks of reality. But Russell's paradox proved that naive set theory was inconsistent, that it allowed contradictions to exist within its structure, and if contradictions are permitted, then anything can be proven true or false, rendering the entire system useless. Russell himself compared the paradox to a barber in a village who shaves all and only those men who do not shave themselves. And the question arises, does the barber shave himself? And if he does, then he should not, because he only shaves men who do not shave themselves. But if he does not, then he must, because he shaves all men who do not shave themselves. And the loop tightens again. Mathematicians scrambled to patch the damage, and various solutions emerged over the following decades. Zermelo and Frankel developed a new version of set theory that imposed strict rules about which sets could exist, forbidding the kind of self-reference that allowed Russell's paradox to form, while type theory introduced hierarchies that prevented sets from containing themselves by assigning different logical levels to different kinds of objects. Others embraced paraconsistent logic, systems that allow contradictions without collapse, or rejected the entire project of grounding mathematics in set theory, seeking new foundations altogether. Russell's paradox also influenced philosophy beyond mathematics, touching on questions of language, meaning, and self-reference, revealing that not all grammatically correct statements are logically coherent, that some sentences create traps from which reason cannot escape. The paradox appears in unexpected places. In computer science, where recursive definitions can cause programs to crash, in legal systems where laws reference themselves in contradictory ways, in everyday thought whenever categories attempt to classify themselves. It stands as a reminder that even the most rigorous systems of thought contain limits, that logic itself is not immune to paradox, that the quest for certainty and completeness may be forever haunted by statements that twist back on themselves and devour their own meaning. Parfit's teletransportation paradox. Imagine a future where technology allows instant travel across vast distances through a process called teletransportation. A device scans your body down to the atomic level, recording the exact position and state of every particle, and then transmits this information to a distant location where another device reconstructs you perfectly, assembling a body atom by atom according to the transmitted blueprint. And the reconstruction is flawless, every memory intact, every scar reproduced, every thought continued, and the reconstructed person steps out of the receiving chamber, believing themselves to be you, feeling no discontinuity, no sense that anything strange has occurred. The philosopher Derek Parfit asked a disturbing question about this process. Are you the person who steps out of the receiving chamber, or did you die in the scanning chamber? And a copy, a duplicate with all your memories and personality, is now living your life. And if the scanning process destroys the original body as it records the information, then perhaps it is still you, continuous in some sense. But what if the original body is not destroyed? What if the scanner leaves you standing in the departure chamber, intact and alive, while the reconstruction appears in the receiving chamber? And now there are two of you, both with equal claim to being the original, both feeling that they are you, and if both are you, then identity has become plural. But if only one is you, then which one and what criterion could possibly distinguish them when they are physically and psychologically identical? Parfit used this thought experiment to challenge the intuition that personal identity is what matters in survival, arguing that what matters is not identity, not being numerically the same person, but rather psychological continuity and connectedness, the preservation of memories, personality, beliefs, desires, and ongoing projects. And if these are preserved, then survival has occurred even if strict identity has not. And so, the reconstructed person is you in every way that matters, even if they are not numerically identical to the original you. And the question of whether identity is preserved is a question about what we care about rather than a deep metaphysical fact. The paradox becomes more troubling when variations are introduced. Suppose the teletransportation device malfunctions and creates not one, but two reconstructions, both perfect, both claiming to be you, and now identity must branch, which seems impossible because identity is supposed to be a one-to-one relation. A thing is identical only to itself, and yet both reconstructions have an equal claim. And if identity is not preserved in this case, then why should it be preserved in the normal case where only one reconstruction appears? And if it is not preserved, then every time you use the teletransporter, you die, and a new person with your memories takes your place, living a life they falsely believe is a continuation of yours. Parfit embraced the conclusion that identity is not what matters, that we should care about psychological continuity rather than numerical identity, and that the concept of a persisting self, a single unified person who endures over time, is less important than we ordinarily think. That what makes your future self matter to you now is not that they are literally the same person, but that they are psychologically connected to you in the right ways. And if those connections can branch or spread across multiple individuals, then so be it. Identity is not sacred, not the ultimate ground of value or concern. The teletransportation paradox has implications for how we think about personal survival, about whether what matters in death is the cessation of psychological continuity or the cessation of biological life, about whether uploading consciousness to a computer or creating digital copies would constitute survival or merely the creation of simulacra, and about whether the self is a metaphysical entity or a convenient fiction we use to organize experience. The paradox also challenges intuitions about moral responsibility, because if identity is vague or plural, then questions about who is responsible for past actions or who deserves future rewards become murky, and the unity of the person, which underpins much of ethics and law, begins to dissolve. Parfit's teletransportation scenario remains one of the most powerful thought experiments in philosophy, a story that uses imaginable technology to expose deep questions about identity, survival, and what it means to be a person, forcing recognition that the boundaries of the self, like the boundaries of clouds and cats, may be far less clear and far less important than common sense suggests, and that the question of whether you survive. Teletransportation may have no determinate answer, or many answers, or may simply be the wrong question to ask. The Achilles and the tortoise. Achilles, the swift-footed hero of Greek legend, agrees to race a tortoise, and to make the contest fair, the tortoise is given a head start, perhaps 100 meters, and the race begins, and Achilles runs swiftly toward the point where the tortoise started. But by the time he reaches that point, the tortoise has moved forward a small distance, perhaps 10 meters, and so Achilles runs toward that new position. But again, by the time he arrives, the tortoise has advanced a bit further, perhaps 1 meter, and this process continues. Each time Achilles reaches where the tortoise was, the tortoise has moved ahead. And it seems that Achilles can never quite catch up, never quite overtake the slower creature. And yet common sense insists that, of course, Achilles will pass the tortoise. That speed wins races, that the faster runner always overtakes the slower, given enough time and distance. And this contradiction between logic and intuition is Zeno's most famous paradox, a puzzle that has captivated philosophers and mathematicians for over 2 millennia. Zeno of Elea constructed this argument in the 5th century BCE as part of his defense of Parmenidean monism, the idea that reality is one unchanging whole and that motion and plurality are illusions. And the paradox was meant to show that the concept of motion leads to absurdity, that if we accept that space and time can be divided infinitely, then the faster can never overtake the slower. And since this conclusion is obviously false, something must be wrong with our assumptions about motion and change. The paradox rests on the idea that Achilles must complete infinitely many tasks, reaching the first point where the tortoise was, then the second, then the third, and so on without end. And if each task takes some amount of time, however small, then infinitely many tasks would require infinite time. And yet in reality, Achilles catches and passes the tortoise in a finite time. And so where is the error? Aristotle argued that the paradox confuses potential and actual infinity, that while the path can be divided into infinitely many segments in thought, Achilles does not actually perform infinitely many separate actions. He simply runs continuously and smoothly, and the infinite division is an artifact of analysis, not a feature of the motion itself. The resolution became clearer with the development of calculus, which showed that an infinite series of diminishing intervals can sum to a finite total, that 1 + 1/10 + 100th, and so on converges to a specific finite value. And so the infinite number of time intervals Achilles requires to reach each successive position also sum to a finite time, the time it takes him to overtake the tortoise. Yet the paradox retains a strange power, a sense that something about infinity remains counterintuitive, that the idea of completing an infinite number of steps feels impossible, even when mathematics insists it is not, and philosophers continue to debate whether the mathematical resolution truly captures the conceptual problem or merely sidesteps it. The paradox also connects to questions about the nature of space and time, whether they are continuous or discrete, whether motion is genuinely smooth or composed of tiny jumps, whether there is a smallest possible distance or duration beyond which reality cannot be divided. And these questions remain open in modern physics, where quantum mechanics and theories of spacetime suggest that the classical picture of smooth continuous motion may break down at the smallest scales. If you enjoy these explorations of paradox and the limits of thought, consider subscribing so you never miss a journey into philosophy's most perplexing puzzles, and perhaps leave a comment sharing where you are in the world as you listen to these ideas unfold. Achilles and the tortoise remain locked in their eternal race, a metaphor for the human attempt to reconcile the finite with the infinite, the continuous with the discrete, the logical with the intuitive. And the paradox endures as a reminder that even the simplest motion, a hero chasing a tortoise, conceals within it mysteries that have not been fully solved. Questions that linger at the boundary where mathematics meets reality, where reason meets experience, where what must be true, according to logic, clashes with what obviously is true, according to the world. The arrow paradox. Motion seems so simple, so obvious. An arrow flies through the air from bow to target, and no one doubts that it moves. Yet the ancient Greek philosopher Zeno of Elea posed a question that has troubled thinkers for over 2,000 years. A question about whether motion is even possible at all. And this is the arrow paradox, one of Zeno's many arguments against the reality of change and multiplicity. Consider an arrow in flight, frozen at a single instant of time. At that precise moment, the arrow occupies a specific region of space exactly equal to its own length and width. It is not in two places at once. It is simply where it is motionless, static, indistinguishable from an arrow at rest. At the next instant, the same is true. The arrow occupies a space equal to itself, motionless at that frozen moment, and at the next instant, and the next. And if time is composed of a sequence of such instants, then at every instant the arrow is motionless. And if the arrow is motionless at every instant, then how can it be said to move at all? For motion would require the arrow to be in more than one place at a single instant, or to be in a state of transition rather than a state of rest, and yet at any given instant there is no motion, only position. Zeno used this paradox to support the Eleatic philosophy of Parmenides, which held that change and motion are illusions, that reality is a single, unchanging whole, and that the apparent diversity and movement we perceive are mere deceptions of the senses. The arrow paradox strikes at the very concept of instantaneous velocity, the idea that an object has a speed at a single moment in time, and Aristotle attempted to refute Zeno by arguing that time is not composed of indivisible instants, but is continuous, that motion is not a series of static positions, but a process that unfolds over intervals, and that the paradox arises only if we mistakenly treat time as a collection of frozen moments, rather than a flowing continuum. Modern physics offers a different resolution through calculus, where velocity is defined as the derivative of position with respect to time, a limit that describes how position changes as the time interval approaches zero. And in this framework, instantaneous velocity is a well-defined concept. The arrow does have a speed at each moment, even though speed is not a property that can be observed in a single instant, but only inferred from the relationship between position and time. Yet some philosophers argue that the arrow paradox still points to something genuine and unresolved, a mystery about how the static and the dynamic relate, how a series of stillnesses can add up to motion, how being in a place can somehow become moving between places. Quantum mechanics adds another layer to the puzzle, because at the subatomic level, particles do not have definite positions and velocities simultaneously. The Heisenberg uncertainty principle states that the more precisely we know a particle's position, the less precisely we can know its momentum. And in some sense, the arrow paradox prefigures this strange quantum behavior, the idea that motion and position are not entirely compatible descriptions of reality. The paradox also connects to debates about the nature of time itself, whether time is discrete or continuous, whether it flows or is an illusion, whether the present moment is all that exists or whether past and future are equally real, and whether change is fundamental or derivative. Zeno's arrow hangs suspended in thought, motionless at every instant, yet undeniably in flight. A puzzle that refuses to vanish despite millennia of analysis. A reminder that even the most basic experiences, the flight of an arrow, the passing of time, the reality of motion, rest on assumptions that can be questioned, that beneath the surface of the obvious lies a tangle of conceptual difficulties that no amount of mathematics or physics has entirely smoothed away, and the arrow flies still, or perhaps it never moved at all, frozen forever in the paradox that bears its name. The analysis paradox. Philosophy has long been concerned with analysis, with taking complex concepts and breaking them down into simpler components, with providing definitions that specify the necessary and sufficient conditions for the application of a term, and this project of conceptual analysis seems both important and straightforward. We want to know what knowledge is, what justice is, what truth is, and we proceed by analysing these concepts, by stating explicitly what they mean, by giving definitions that capture their essential features. Yet there is a paradox lurking here, a puzzle about whether analysis is even possible. And this is the paradox of analysis, first articulated clearly by C.H. Langford, and discussed extensively by G.E. Moore and others in the early 20th century. The paradox can be stated simply: suppose we offer an analysis of some concept. For example, we might analyse the concept brother as male sibling, and this analysis, if correct, should be informative, should tell us something we did not already know about what brotherhood consists in, should illuminate the concept by making its structure explicit. But if the analysis is correct, then the analysandum, the concept being analysed, and the analysans, the analysis itself, must have the same meaning. They must be synonymous, otherwise the analysis would be incorrect. It would not capture what brotherhood really is. And if they are synonymous, then the statement brother means male sibling should be trivial, should be like saying brother means brother, a mere tautology that provides no new information. And so the analysis cannot be both correct and informative. If it is correct, then it is trivial. And if it is informative, then it is not a genuine analysis, but merely a stipulation or a proposed change of meaning. The paradox threatens the entire project of conceptual analysis, because it suggests that analysis cannot do what it is supposed to do, cannot both correctly identify the meaning of a concept and provide new insight into that meaning, cannot be both true and interesting, and so either conceptual analysis is impossible, or our understanding of what analysis is and what it aims to achieve must be revised. One response to the paradox distinguishes between sense and reference, between the meaning of a term and what it picks out, and argues that an analysis can be informative even if the analysandum and analysans refer to the same thing, because they can differ in sense, in the way they present or describe that thing. And so the analysis brother means male sibling is informative, because even though brother and male sibling refer to the same set of individuals, they present that set in different ways, one as a family relation and the other as a combination of gender and kinship. And this difference in sense makes the identity statement informative rather than trivial. Another response appeals to a distinction between conceptual and factual knowledge, arguing that analysis does not provide factual knowledge about the world, but conceptual knowledge about our own concepts, that it makes explicit what was already implicit in our understanding, that it brings to consciousness the structure of concepts that we already possess and use, but have not fully articulated. And so, the informativeness of analysis is not the informativeness of discovering new facts, but the informativeness of self-clarification, of making our own conceptual commitments explicit and transparent. A third response associated with Quine and others skeptical of the analytic-synthetic distinction denies that there is a sharp line between conceptual analysis and empirical investigation, arguing that all beliefs form a holistic web where conceptual revisions and factual discoveries are intertwined, and that what we call analysis is really just careful reflection on our current best theory of the world, subject to revision in light of new evidence or theoretical considerations. And on this view, the paradox dissolves because analysis is not supposed to be a priori or purely conceptual, but is continuous with empirical inquiry, and so it can be both correct and informative without any mystery. The paradox also raises questions about the methodology of philosophy, about whether philosophy can make progress through analysis or whether some other method is needed. And different philosophical traditions have taken different stances, with analytic philosophy traditionally emphasizing conceptual analysis as a central tool, while continental philosophy has been more skeptical of analysis, focusing instead on interpretation, critique, and phenomenological description. And the paradox of analysis has been one factor driving some philosophers away from traditional analysis toward other approaches. The paradox connects to issues about understanding and competence, because we seem to have a kind of implicit or tacit understanding of concepts like knowledge, justice, and truth. We can use these concepts correctly, can apply them to particular cases, can recognize when they are used inappropriately, and yet when asked to state explicitly what these concepts mean, to provide a definition, we struggle. And this suggests that conceptual competence does not require explicit knowledge of definitions, that understanding can be practical and procedural rather than theoretical and propositional, and that analysis attempts to convert implicit understanding into explicit knowledge, a conversion that is difficult and perhaps impossible to complete without remainder. The paradox also appears in the context of philosophical disagreement, because philosophers have been offering analyses of key concepts for millennia, and yet consensus remains elusive. Different philosophers provide different analyses of knowledge, of justice, of truth, and it is not always clear how to adjudicate between competing analyses, whether by appeal to intuitions about particular cases, by considerations of theoretical simplicity and fruitfulness, or by some other standard. And the lack of agreement raises the question of whether these concepts have determinate meanings that analysis can discover, or whether they are vague, contested, or essentially contested, such that no single analysis could capture all the ways they are legitimately used. The analysis paradox remains a puzzle at the heart of philosophy, a question about what philosophy is doing when it offers definitions and analyses, whether it is discovering pre-existing meanings, stipulating new ones, or engaging in some more complex activity that combines elements of discovery, stipulation, and rational reconstruction, and the paradox has not been definitively resolved. Different philosophers find different responses more or less compelling, and the debate continues, with implications for how we understand the nature and methods of philosophical inquiry. And the concept sits there, waiting to be analysed, inviting us to state its essence, to specify its conditions, to make explicit what we already implicitly know, and yet the analysis, when offered, seems either to tell us nothing new or to change the subject, to offer a different concept rather than clarifying the original one. And the paradox persists, a thorn in the side of analysis, a reminder that understanding is more elusive than it appears, that the gap between knowing how to use a concept and knowing what it means is wider than we thought, and that philosophy, despite its ancient commitment to clarity and definition, to making the implicit explicit and the confused clear, may be chasing a goal that is inherently problematic, inherently paradoxical, a goal that recedes as we approach it, that becomes more obscure the more we try to illuminate it, and yet we continue to analyse, to offer definitions, to seek clarity, because the alternative, giving up on understanding, seems worse. Skolem's paradox. Set theory describes infinite sets of different sizes, and Georg Cantor proved that the real numbers are uncountably infinite, that they cannot be placed in one-to-one correspondence with the natural numbers, that there are more real numbers than natural numbers, and this is one of the foundational results of modern mathematics. a theorem that establishes a hierarchy of infinities. But Thoralf Skolem discovered a paradox, or what appears to be a paradox, that threatens this result. And the paradox is that any consistent first-order theory that has an infinite model also has a countable model, a model where the domain consists of only countably many elements. And this is the Löwenheim-Skolem theorem, and applying it to set theory yields a troubling conclusion. If set theory is consistent, then it has a countable model, a model where the universe of sets is countably infinite. And yet within this model, the axioms of set theory are satisfied, including Cantor's theorem, which proves that the real numbers are uncountable. And so we have a countable model of set theory in which there exists an uncountable set. And this seems contradictory. How can a set be uncountable if the entire universe is countable? How can there be more real numbers than natural numbers if the whole model has only countably many elements? And this is Skolem's paradox. The resolution lies in understanding the distinction between internal and external perspectives, between how things appear from inside the model and how they appear from outside. From inside the countable model of set theory, all the axioms hold. Cantor's theorem is provable. The real numbers have no enumeration within the model. No bijection between the reals and the naturals exists as far as the model is concerned, and so internally the reals are uncountable. But from outside the model, from the perspective of someone who can see the entire structure, the model itself has only countably many elements, and there exists a bijection between the elements of the model and the natural numbers, a bijection that is not itself an element of the model, that does not correspond to any set or function within the model. And so externally, the model is countable. And this distinction between internal and external is the key to resolving the paradox. Uncountability is relative. It depends on what bijections are available, and different models have different bijections. Skolem's paradox reveals something profound about the nature of mathematical existence and the limits of first-order logic. It shows that first-order logic cannot pin down the cardinality of infinite sets, that the concept of uncountability is not absolute but relative to a model, that what counts as uncountable in one model may be countable in another, and this relativity is a consequence of the expressive limitations of first-order logic, which can only quantify over elements of the domain, not over arbitrary functions or sets of elements. And so first-order set theory cannot express the existence of a bijection between two sets in an absolute way, cannot say, in a model-independent manner, that a set is countable or uncountable. Some philosophers and logicians find this relativity troubling, a sign that first-order set theory is inadequate as a foundation for mathematics, that a stronger logic, perhaps second-order logic, which allows quantification over sets and functions, is needed to capture the intended meaning of set theoretic concepts. And in second-order logic, the Löwenheim-Skolem theorem does not hold. There are categorical characterizations of structures, including characterizations of the natural numbers and the real numbers that pin down their cardinality uniquely. And so second-order logic avoids Skolem's paradox by being more expressive, by allowing statements that distinguish countable from uncountable models. But second-order logic has its own difficulties. It lacks complete proof systems. There is no algorithmic procedure that can, in principle, prove all second-order truths. And so the gain in expressiveness comes at the cost of losing some of the nice logical properties that first-order logic enjoys. Others embrace the relativity revealed by Skolem's paradox, arguing that it shows the conventional or perspectival nature of mathematical concepts, that cardinality is not an intrinsic property of sets but a relation between sets and models, that what we call uncountable is simply a set that lacks an enumeration within a particular model, and that different models can disagree about what is countable without any of them being wrong. And this perspective aligns with a pluralistic or model-theoretic approach to mathematics, where there is no single intended model of set theory, but many models each with its own internal structure, and what is true varies from model to model, and mathematical truth is relative to a choice of model. Scolam's paradox also connects to issues about the definiteness of the continuum, about whether the set of real numbers has a well-defined cardinality, and the continuum hypothesis, which asks whether there is a set whose cardinality is strictly between that of the natural numbers and the real numbers. And this hypothesis is independent of the standard axioms of set theory, meaning that neither the hypothesis nor its negation can be proven from the axioms. And some mathematicians interpret this independence as evidence that the cardinality of the continuum is not a definite matter of fact, but depends on additional assumptions or on the choice of model. And Scolam's paradox reinforces this interpretation by showing that even the distinction between countable and uncountable is model dependent. The paradox remains a touchstone in the philosophy of mathematics and the foundations of logic. It illustrates the limits of first-order logic, the relativity of model theoretic notions, and the gap between formal systems and intended interpretations. And it forces careful thinking about what it means to say that a set is countable or uncountable, about whether mathematical concepts have absolute meanings or are always relative to a framework, and about the relationship between syntactic provability and semantic truth. And the paradox has no simple resolution. Different philosophers and mathematicians draw different lessons, some seeing it as a defect of first-order logic, others as a feature revealing deep truths about the nature of infinity and cardinality. And the debate continues, with implications for how we understand the foundations of mathematics, the status of set theory, and the nature of mathematical truth. The countable model sits in logical space, containing sets and functions and real numbers, and within this model, Cantor's theorem holds. The reals are uncountable, no enumeration exists, but from outside the model, the whole structure is countable, all its elements can be listed, and the real numbers of the model, uncountable internally, are countable externally. And this doubling of perspective, this split between internal and external, is the heart of Scolam's paradox, a demonstration that perspective matters, that truth is not always absolute, that models can disagree, and that first-order logic, powerful as it is, cannot capture all the nuances of infinite cardinality. And the paradox endures, a puzzle that has shaped logic and set theory, a challenge that continues to generate discussion and debate, and a reminder that even the most basic mathematical concepts, even the notion of how many, become subtle and contested when applied to infinite collections. The barber paradox. In a small village, there lives a barber who follows a single rule. He shaves all and only those men in the village who do not shave themselves. And this rule seems simple enough until the question emerges: does the barber shave himself? And suddenly the logic collapses into contradiction. If the barber shaves himself, then he belongs to the group of men who shave themselves, which means according to the rule, he should not shave himself because he only shaves men who do not shave themselves. But if he does not shave himself, then he belongs to the group of men who do not shave themselves, which means according to the rule, he must shave himself because he shaves all men who do not shave themselves, and the loop tightens without escape, spinning endlessly between two impossible options. Bertrand Russell popularized this version of his own paradox as a way to make the abstract problem of self-referential sets more accessible, more human, more vivid, because a barber is easier to imagine than a set of all sets that do not contain themselves. Yet the logical structure remains identical, a rule that turns inward and devours its own coherence. The paradox reveals something unsettling about definitions and categories, that not all rules can be consistently applied, that language and logic can conspire to create situations that seem perfectly reasonable until examined closely, and then they shatter. Some philosophers argue that the barber simply cannot exist, that the rule itself is contradictory, and therefore no such barber could ever follow it in reality, while others suggest that the problem lies in assuming the rule must apply universally, that perhaps the barber is exempt from his own rule, or that the village contains no barber at all. The paradox also exposes the danger of self-reference, the way that statements or rules that loop back on themselves can generate infinite regress or outright contradiction. And this has implications far beyond barbershops, touching mathematics, computer science, law, and any system that attempts to regulate itself from within. In set theory, the barber paradox mirrors Russell's discovery that naive set theory permits the construction of sets that cannot exist without contradiction, forcing mathematicians to impose restrictions on which sets are allowed to form, creating hierarchies and boundaries to prevent self-reference from poisoning the system. The barber stands at the edge of reason, a figure trapped in a loop of his own making, unable to shave or not shave without violating the very rule that defines his existence, and in this way, he becomes a symbol of the limits of logic, a reminder that not every question has an answer, that some problems resist resolution no matter how carefully they are examined. The paradox lingers in the mind, a simple story about a man and a razor that somehow reveals a crack in the foundation of thought itself, and once noticed, it cannot be ignored, appearing again and again wherever rules turn inward, wherever systems attempt to contain themselves, wherever language reaches the boundary of what it can coherently express. The Bertrand's box paradox. 3 identical boxes sit before you, each containing 2 coins. The first box contains 2 gold coins, the second box contains 2 silver coins, and the third box contains 1 gold coin and 1 silver coin. And you cannot see inside the boxes, cannot distinguish them from the outside. And a box is chosen at random and opened, and 1 coin is drawn from it, also at random, and the coin turns out to be gold. And now a question is posed that seems simple, but leads to surprising confusion. What is the probability that the other coin in the same box is also gold? And the intuitive answer that most people give is 1/2, reasoning that since the drawn coin is gold, the box cannot be the one with 2 silver coins. So it must be either the box with 2 gold coins or the box with 1 gold and 1 silver. And these 2 possibilities seem equally likely, and so the probability that the other coin is gold should be 1/2. But this reasoning is wrong. The correct answer is 2/3, and this is Bertrand's box paradox, named after Joseph Bertrand, who presented it in 1889, a puzzle in conditional probability that reveals how easily intuition misleads when reasoning about random processes and conditional information. The error in the intuitive reasoning lies in treating the 2 remaining boxes as equally likely, but they are not, because the probability calculation must account for how the gold coin was observed, must condition not just on which box was chosen, but on which coin was drawn. And the key insight is that there are 3 gold coins in total, 2 in the first box and 1 in the third box, and the drawn coin is equally likely to be any of these 3. And if the drawn coin is one of the 2 from the first box, then the other coin in the same box is also gold, while if the drawn coin is the one from the third box, then the other coin is silver. And since 2 of the 3 equally likely possibilities lead to the other coin being gold, the probability is 2/3, not 1/2. Another way to see the solution is to consider all possible outcomes. There are 6 coins in total, labelled gold 1 and gold 2 in the first box, silver 1 and silver 2 in the second box, and gold 3 and silver 3 in the third box, and each coin is equally likely to be the one drawn, and we're told that a gold coin was drawn, which eliminates silver 1, silver 2 and silver 3, leaving gold 1, gold 2 and gold 3 as equally probable. And if gold 1 was drawn, then the other coin in the same box is gold 2. If gold 2 was drawn, then the other coin is gold 1. And if gold 3 was drawn, then the other coin is silver 3. And so in 2 of the 3 cases, the other coin is gold, giving a probability of 2/3. The Bertrand box paradox is structurally similar to other probability puzzles, like the Monty Hall problem and the three prisoners problem, where conditioning on partial information updates probabilities in non-obvious ways, where the process by which information is revealed matters as much as the content of the information, and where naive intuition fails to properly account for the structure of the problem, and the paradox illustrates the importance of specifying the sample space carefully, of identifying all possible outcomes and their probabilities, and of using Bayes' theorem or other formal tools to update probabilities rather than relying on informal reasoning. The paradox also raises questions about the reference class problem, about which population of events the observed outcome should be considered a member of, because the intuitive error involves thinking of the outcome as selecting a box type, either 2 gold or mixed, rather than selecting a particular coin, and this shift in reference class changes the probabilities, and the correct solution requires identifying the right reference class, the set of all coins that could have been drawn, and calculating probabilities relative to that set. Bertrand's box paradox has pedagogical value. It is often used in teaching probability to illustrate conditional probability, to show how careful reasoning differs from intuitive judgment, and to demonstrate the value of systematic methods like constructing probability trees or using Bayes' theorem, and students who understand the paradox gain insight into a common class of errors that arise from failing to properly condition on all relevant information, from treating distinct events as equiprobable when they are not, and from confusing the probability of a hypothesis given evidence with the probability of evidence given a hypothesis. The paradox also appears in variations, sometimes with coloured balls instead of coins, sometimes with different numbers of boxes or different distributions, and each. Variation tests slightly different aspects of probabilistic reasoning, but the core lesson remains the same, that conditional probabilities must be calculated carefully, that intuition is unreliable, and that formal methods are necessary to avoid systematic errors. And the paradox connects to real-world situations where similar reasoning is required. Medical diagnosis, where symptoms must be interpreted in light of disease prevalence and test reliability. Legal reasoning, where evidence must be weighed in light of prior probabilities and alternative explanations. And machine learning, where classifiers must be trained to properly account for base rates and conditional dependencies. The boxes sit on the table, indistinguishable from the outside. The gold coin gleams in your hand, and the question hangs in the air: what is the probability that the other coin is also gold? And the answer, 2/3, contradicts the intuitive 1/2, and the gap between intuition and mathematics reveals something about how we reason about chance, about how we estimate probabilities, about how we update beliefs in light of evidence. And the Bertrand box paradox remains a touchstone, a simple puzzle with a surprising answer, a demonstration that probability is subtle, that conditioning changes things in non-obvious ways, and that even questions that seem straightforward can hide complexity, can require careful analysis to answer correctly. And the paradox endures as a teaching tool, a cautionary tale, a reminder that mathematical reasoning is necessary to avoid errors that intuition cannot prevent. And the gold coin sits there, evidence that shifts probabilities, information that updates beliefs, and the calculation proceeds, formal and precise, yielding 2/3, and the intuition retreats, humbled by mathematics, corrected by careful thought, and the lesson is learned again, that probability is counterintuitive, that conditional reasoning is hard, and that paradoxes like Bertrand's box serve an essential function, exposing the gaps between how we think we reason and how we actually should reason, between the quick judgments of intuition and the slow calculations of mathematics. And the boxes remain coins inside, waiting to teach the next student, to confound the next intuition, to reveal once more that chance and evidence interact in ways that defy expectation, and the paradox persists, elegant and instructive, a permanent fixture in the pedagogy of probability, a puzzle that generations of students have encountered and been surprised by, and will continue to encounter as long as probability is taught and intuition needs correction. The binding problem: how your brain unites what it processes separately. A neuroscientist examines how the brain processes visual information, discovers that different features of objects are processed in different brain regions. Color is processed in one area, motion in another, shape in a third, orientation in a fourth, and all these features are analyzed separately, by specialized modules, by distinct populations of neurons. And yet when you look at a red ball moving to the right, you do not experience color, motion, and shape as separate. Do not see redness here and roundness there and rightward motion elsewhere, but see a unified object, a red round ball moving right, and all the features are bound together, are experienced as properties of a single thing. And this creates the binding problem, the puzzle of how the brain, which processes features separately, creates unified conscious experiences, how separate neural processes give rise to integrated perception, how the many become one. And this problem is fundamental, touches on the nature of consciousness, on how neural activity becomes experience, on what unifies experience into coherent wholes, and no complete solution exists. Various theories have been proposed, but the binding problem remains one of the deep mysteries of neuroscience, a gap between our understanding of neural processing and our understanding of consciousness. Imagine the visual system as a factory, with different departments processing different aspects of the product. One department handles color, another handles shape, another handles location, and all work in parallel, all process simultaneously, and each department produces its output color information, shape information, location information, and somehow these separate outputs must be combined, must be integrated into a unified representation, must be bound together so that you experience a red ball rather than redness and roundness as separate unlocalized features. And the binding problem asks how this combination occurs. What mechanism ensures that the right features are bound together, that the redness is attributed to the round object and not to the square object that happens to be present in the scene. And this correct attribution, this accurate binding, is critical for coherent perception, for navigating the world successfully, and yet how the brain achieves it remains unclear. The binding problem has two aspects: the feature binding problem, which asks how different features of the same object are bound together, and the object binding problem, which asks how different objects are kept separate, are not confused with each other, and both aspects are challenging. Both reveal that perceptual unity is not given automatically by neural processing, but requires some mechanism, some process that groups features appropriately, and various mechanisms have been proposed. Attention has been suggested as a solution. The idea that attention binds features, that attended objects have their features integrated, while unattended objects do not. And this explains why feature binding errors occur when attention is diverted, why illusory conjunctions occur where features from different objects are misbound, are attributed incorrectly. Visualize attention as a spotlight that illuminates objects one at a time, and within the spotlight features are bound, are integrated, and outside the spotlight features remain separate, are not integrated. And this attentional binding theory has some support, has experimental evidence showing that feature binding requires attention, that without attention, features can be perceived separately without being bound correctly, and illusory conjunctions are more common under conditions of inattention, supporting the idea that attention is necessary for binding. But attention cannot be the complete solution, because some binding occurs pre-attentively. Some feature integration happens automatically before attention is applied, and so attention is part of the story but not the whole story. Another proposed mechanism is temporal synchrony, the idea that neurons representing features of the same object fire in synchrony, fire together, and this synchrony is the binding code, is what marks features as belonging together and neurons representing different objects, fire at different times or with different phases, and this temporal separation keeps objects distinct, prevents their features from being bound together. And this synchrony theory has been influential, has generated extensive research, has led to discovery of synchronized neural oscillations in visual cortex, but the theory faces challenges. It is not clear that synchrony is sufficient for binding, it is not clear that consciousness depends on synchrony, and some experiments have failed to find the predicted correlations between synchrony and perceptual binding, and the theory remains controversial. A third approach argues that binding occurs through convergence, through hierarchical processing, where features are combined in higher-level areas, and early visual areas process features separately, but project to higher areas that represent combinations, that have neurons responding to specific conjunctions of features. And these conjunction neurons represent bound objects, represent integrated wholes, and binding is achieved through this hierarchical architecture, through neurons that explicitly encode feature combinations. And this approach has support from single neuron recordings showing that higher visual areas have neurons with complex selectivity, neurons that respond to specific combinations of shape and color and motion, and these neurons could be the neural basis of bound object representations. The binding problem also connects to consciousness, because unified conscious experience seems to require binding, seems to require that separate neural processes be integrated into coherent wholes, and some theories of consciousness, like integrated information theory, make integration central, argue that consciousness arises from integrated information, from systems where different parts interact and constrain each other, and binding as a form of integration is the combination of separately processed features into unified representations. And understanding binding may be crucial for understanding consciousness, may reveal how neural processes give rise to unified experience. The problem also has practical implications. For understanding neurological conditions where binding fails, where patients see features but cannot bind them correctly, and such conditions exist. Barlint's syndrome is one example, where patients can see individual features but cannot perceive objects, cannot integrate features into wholes. And these patients provide evidence that binding is a genuine process, is not automatic, can be disrupted by brain damage. And studying these patients helps understand normal binding, helps identify the brain regions and processes necessary for feature integration. Some philosophers argue that the binding problem is really a problem about consciousness, about how physical processes give rise to subjective experience, about the hard problem, and binding is one aspect of this, is the problem of how separate neural processes give rise to unified conscious experiences. And solving the binding problem may require solving the hard problem, may require understanding how neural activity becomes experience. And this makes binding one of the deepest problems in neuroscience, a problem at the interface between neuroscience and philosophy of mind. The brain processes features separately, color here, motion there, shape elsewhere, and yet you see unified objects, see red round balls moving, see integrated wholes, and how this integration occurs, how the separate processes give rise to unified experiences, remains one of the great unsolved problems. The binding problem stands, challenging, fundamental, revealing a gap between our understanding of neural processing and our understanding of perception. And various theories exist, various mechanisms have been proposed. Attention, synchrony, convergence, but no theory is complete. No theory explains all aspects of binding, and the problem persists as one of neuroscience's deepest mysteries. A puzzle about how unity emerges from multiplicity, how the brain binds what it processes separately, and the question remains open. the mechanism remains elusive, and the binding problem endures. The bootstrap paradox. There exists a strange loop in time where cause and effect chase each other in a circle, where information or objects appear from nowhere, with no origin, no creator, no beginning, and this is the bootstrap paradox, named after the impossible act of pulling oneself up by one's own bootstraps, a paradox that emerges whenever time travel creates a causal loop that has no starting point. Imagine a time traveler who loves a particular symphony, and one day they decide to travel back in time to meet the composer, but when they arrive in the past, they discover that the composer has not yet written the symphony, and so the time traveler, eager to hear the music again, writes down the notes from memory and gives them to the composer, who then publishes it as their own work, and the symphony becomes famous, and years later the time traveler hears it and falls in love with it and decides to travel back in time to meet the composer, and the loop is complete. The question that haunts this scenario is simple and unanswerable. Who actually composed the symphony? The composer received it from the time traveler, and the time traveler received it from the composer, and neither of them created it. The information simply exists within the loop, passed from future to past and back again, with no point of origin, no moment of creation, no author. The bootstrap paradox differs from the grandfather paradox because it does not involve contradiction. The timeline is perfectly self-consistent. Every event follows logically from every other event. There is no clash between cause and effect, and yet something feels deeply wrong, an intuition that things must come from somewhere. That information cannot simply exist without being created. The paradox appears in many variations: a book that writes itself, a watch that is given to a younger version of oneself, who then keeps it for decades before giving it back, a technology that is brought from the future and used to invent itself, and in each case the object or information becomes eternal, trapped in a loop of time, aging perhaps, but never truly beginning or ending. Some physicists accept the bootstrap paradox as a genuine possibility if time travel is real, arguing that closed time-like curves, paths through space-time that loop back on themselves, are permitted by general relativity under certain conditions, and that such loops might allow for causally self-sufficient systems where the past and future are mutually dependent. Others find the paradox deeply troubling, a sign that something is wrong with our understanding of causation, entropy, or time itself, because information in a loop would violate the second law of thermodynamics, which states that entropy always increases, that order does not arise spontaneously from disorder, and yet in a bootstrap loop, the information appears to be perfectly preserved, never degrading, never increasing in entropy, existing in a kind of timeless stasis. The many worlds interpretation offers one way out, suggesting that the time traveler who delivers the symphony creates a new branch of reality, and that in their original timeline, the symphony had a different origin, but this solution feels like cheating, multiplying universes to avoid the discomfort of the loop. The bootstrap paradox forces confrontation with deep questions about the nature of causation, whether causes must always precede effects, whether the universe permits closed causal loops, and whether existence itself requires an ultimate origin, or whether some things can simply be eternal and self-caused, through time without beginning or end, defying the intuition that everything must come from something, that there must always be a first cause, a prime mover, a starting point from which all else flows.